This last section is about oxidation-reduction reactions. So in an oxidation-reduction reaction, we have electrons that are transferred from one reactant to the other. Oxidation-reduction, a whole bunch of syllables, and so we often call these redox reactions. Read for reduction and ox for oxidation. It looks like Redox, which used to make me think of Redbox, but that's not really much of a thing anymore. Anyway, redox reactions. A lot of redox reactions involve something reacting with oxygen. And that's where the idea of oxidation first came about, is when something reacts with oxygen, it's oxidized. So here's a couple of examples. Iron reacting with oxygen to form Fe2SO3. Here we have octane reacting with oxygen. This is a combustion reaction, forming CO2 and water. We can even have hydrogen reacting with oxygen gas to form water. These are all redox reactions. Here we have a balloon filled with hydrogen and oxygen gas mixed together. And if you give that a little spark, it goes kaboom, right? Just big fireball here. Very exothermic reaction. I don't recommend doing that.
Yeah, but then people make up those giant blimps.
Well, the giant blimps actually are not as dangerous as this type of a balloon. So you've probably heard of the Hindenburg blimp filled with hydrogen, right? Turns out that wasn't a great idea. So the Hindenburg went up in flames because the hydrogen, there was some spark or something that set it off, and so it burned. And that was a disaster. But if there had been hydrogen and oxygen gas mixed together in the blimp, it would have been much, much worse. When I was in college, we had a chemistry club, and we put on a show. And I remember one show we had a balloon full of oxygen, and we had a balloon full of hydrogen, and we had a balloon with a mix of oxygen and hydrogen. And so you tape a candle literally to the end of a meter stick, because you don't want to be too close to this. And you light the pure hydrogen balloon, and it gives this nice pop sound. And you light the oxygen one, and that kind of goes poof. And then they lit the one that was mixed, and this was in a big lecture hall, bigger than S70 downstairs. And it made all the ceiling tiles jump. It was kaboom from a single balloon. No, we don't need to try that. It's dangerous. But when the gases are already mixed, they burn much more quickly, because you have to have the oxygen and the hydrogen together. The Hindenburg burned kind of from the outside in as oxygen from the air mixed with the helium in the balloon.
Is it because oxygen is a major catalyst of flame, or like what's the main?
Well, combustion is the reaction of something with oxygen. Mm-hmm. So you can't have combustion without oxygen.
So is that why I went from outside in with the Hindenburg, because oxygen started flowing in?
Yeah, because there was no oxygen inside the Hindenburg. It was just hydrogen. And hydrogen by itself cannot explode or do anything. But if it's in contact with oxygen and gets a spark, then it'll start, and then it just kind of snowballs from there. And so that's why they fill blimps with helium now instead of hydrogen. Lesson learned. Here's another redox reaction. This one is not a combustion reaction, mixing sodium, the element, and chlorine, the element, and these will react quite vigorously as well, and they'll form sodium chloride. So what's happened here is we had sodium atoms and chlorine molecules, and electrons are transferred from the sodium atoms to the chlorine atoms, forming ions. So there's a transfer of electrons, and we end up with an ionic compound. So that's what we just looked at, sodium plus chlorine to make sodium chloride. We can also have sodium reacting with oxygen. That'll make a sodium oxide. So this is metal reacting with a nonmetal. These are both oxygen. We can also have reactions, well, this one is the same, but so the conversion of free elements into ions, so sodium and oxygen forming sodium oxide, right? So the sodium atoms become ions by losing an electron. The oxygen atoms become ions by gaining electrons. So that's an oxidation reduction. In order for those atoms to become ions, we have to gain or lose electrons. If one atom loses an electron, something else has to gain the electron. You don't have atoms just shedding electrons, and where do the electrons go? They're sleeping on the streets, or they're going to the SPCA pet shelter for electrons. No, that doesn't happen. If there's not another atom to take the electron, it doesn't leave the first atom. So oxidation and reduction always go together. So atoms that lose electrons are said to be oxidized. Atoms that gain electrons are said to be reduced. So here we have sodium going to Na+. It does that by losing an electron. Chlorine gains electrons to become chloride. And so this is another one of those pairs of things we have to remember. And this little mnemonic here, oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Unless you use these terms all the time, it's really kind of hard to keep them straight. And I teach this stuff every semester, but in between, I don't think about it very much. And so when I identify an oxidation or a reduction, in my head, I'm thinking oil rig, because otherwise I'm going to get confused. So that was forming actual ions from atoms, a complete transfer of electrons from one atom to another. It doesn't have to actually be a complete transfer. It can be sort of a shift in the electron density. So if we're looking at the reaction between hydrogen gas and chlorine gas, it's going to form hydrogen chloride gas. In the hydrogen and chlorine molecules, they have two identical atoms. The electrons are equally distributed. There's no positive or negative end. In the HCl molecule, the chlorine is more electronegative than the hydrogen, and so it kind of pulls the electrons away, kind of like hogging the blankets when you're sharing a bed with a sibling, right? Chlorine's the blanket hog, and so it's pulling the electrons away. This end is partially negative, this end is partially positive. So oxidation reduction has occurred here, it's just not a complete transfer. So here the chlorine has increased its electron density. It didn't actually gain an electron, but it gained electron density, right? So reduction is gain. Oxidation is loss. The hydrogen here has lost electron density, and so the hydrogen is being oxidized. So redox reactions between two nonmetals are more difficult to identify. When we look at combustion or reactions where ions are formed, we can see, yes, that's gained oxygen, that is, become ions, we can identify what's going on. How do we tell, like with the H2 plus Cl2, how do we tell that it's a redox reaction, and how do we identify which one is oxidized or reduced? Well, we use a made-up concept called oxidation state, sometimes called oxidation number. So we assign an oxidation state to each element to help us figure out where the electrons or the electron densities are going. Now, it's very important to understand that oxidation states are not ion charges. They're not actual charges. Those are imaginary charges. What's confusing is that oxidation states are often the same number as the ionic charge, but they are not the same thing. Ion charges are real measurable charges. Oxidation states are imaginary. We made them up. So there's rules for assigning oxidation states. And as with many things, when you write out all the rules, they look very complicated. If if there's a board game that you really enjoy playing, and then you go look at the rules, you know how to play it, but then you go read the rules, oh my goodness, it's confusing, right? You try to play a new game, you read the rules, and you're like, I don't know. It's really hard. So these rules make it look really hard. It's actually not that bad. So free elements have an oxidation state of 0. Well, the way I think of that is, what is the charge on this copper atom all by itself? It doesn't have a charge, right? And here we have a free element, chlorine. It's a molecule, but it's a diatomic molecule. Both atoms are the same. There's no charge imbalance. Free elements are always 0. If we have a monatomic ion, the oxidation state is the same as the charge. So calcium 2+, the oxidation state is the same as the charge. So this would be +2. For chloride, it would be -1. The sum of oxidation states of all the atoms in a neutral compound is 0. In an ion, it equals the charge of the ion. So that's just how ion charges worked, right? If you're putting two ions together, the overall charge on the thing would be the sum of the ion charges. We're doing the same thing here. The sum of the oxidation states will equal the overall charge. So these guys are going to add up to 0. Oxidation states on this is going to add up to -1. In their compounds, metals have positive oxidation states equal to their ion charge. I'm not sure why we even really need to say that, because monatomic ions have an oxidation state equal to their charge. It's the same thing, right? So chlorine ion +2, here's sodium ion +2, right? So all of those are very similar to what the charges are. The only part that's different is, what about the nonmetals? You look at a compound like H2O, and it's a molecular compound. There aren't any charges. How do you tell where the electron density is? Well, you look at the oxidation states. So these are the rules for that. Y'all know what pho is, right? Food, really good noodles, right? Yum. Let's go get some. Well, if I just cut off the P in pho, that would still probably say pho, right? So this is how I remember this chart. Fluorine, hydrogen, oxygen. Actually, I didn't leave enough space for myself. Pho 765. There's actually a restaurant, Pho 76. Anyway, Pho 765. Fluorine, hydrogen, oxygen, group 7, group 6, group 5. That's not too hard to remember. Pho 765. So when we're looking at the nonmetals in compounds, what we're going to do is, this is the order in which they get to pick their oxidation state. That's how I think of it. What oxidation state are they going to pick? They're going to choose the oxidation state that would be their ion charge if they were an ion, right? So if fluorine becomes an ion, its charge would be -1. Fluorine gets to choose first. It's going to choose the oxidation state equal to its charge if it was an ion. Next is hydrogen. What kind of an ion does hydrogen form? +1. That's the oxidation state that hydrogen would like to have. Oxygen is third choice. Oxygen ions, oxide ions, have a -2 charge. And then we go to elements in group 7. Those are the halogens. They would have -1 charges. Group 6, -2. Group 5, -3. So Fe765, fluorine, hydrogen, oxygen, group 7, group 6, group 5. That's the order that you look at the elements when you just have nonmetals. The oxidation state that they pick is the same as they would have an ion charge. And after you get through all but the last one, then the last element has to be whatever is necessary to make up the overall charge on the molecule. So we can have fractional oxidation states because these are made up. You can't have like a 1/2 charge on an ion, but you could have a 1/2 oxidation state. I don't think we're going to see any in Chem 1A though. And just so you're not confused, in oxidation states we write the sign before the number, and for ion charges we write it after the number. I'm not going to try to trick you on that one, but I just want you to know why we're doing that. So these are oxidation states, right? The charge on a fluoride ion, the charge is, it's F- or 1-. Oxygen is 2-, not -2. But the oxidation state, we switch them. Not a big deal. Okay. Assign an oxidation state to each atom in each element, ion, or compound. So each atom is going to have an oxidation state. So this first one, we have a chromium atom. Well, does this thing actually have a charge? No, it doesn't. And there's only the one element there. Overall, it has to be 0. There's only one thing there, right? So its oxidation state is 0. All free elements have 0 as their oxidation state. Here we have the Cr3+ ion. What's its oxidation state? It's the same as the charge, +3. So the oxidation state for that one is +3. Here we have carbon tetrachloride. There's a carbon and 4 chlorine atoms. Okay, so now we get out Fe765. And we're looking at these elements. Is there fluorine? Nope. Hydrogen? Nope. Oxygen? Nope. Group 7 element? Yeah, chlorine. What is chlorine going to pick? -1. Right? So the chlorine chooses -1. I guess I really shouldn't write it like that. The chlorine is going to choose -1. Each of these chlorines is going to have a -1 charge. So maybe it'd be helpful to write all of them out. So each of them is going to have a -1 charge. Oxidation state. So then what's the oxidation state on the carbon? +4. So the carbon would have to be +4. Because like ion charges, this is a neutral molecule. All of the oxidation states have to add up to the overall charge, which is 0. Okay, so it's a lot like ion charges, hence the warning, don't think that these are ion charges. Okay, SrBr2. Well, this is an ionic compound, right? It actually has ions in it. So the oxidation states are the ion charges. So the oxidation state for strontium in there will be +2 because it's group 2A. And how about the bromine? It'll be -1. And there's 2 of them, right? Each of them is -1. So then we see that the oxidation states add up to the overall charge. Yeah.
Do we actually write like, so for C and D, when you wrote the chlorines 4 times and bromines 2 times, do we actually do all that too?
No, you do not have to write the chlorines 4 times. I'm doing that here in the beginning just to make it clearer why carbon is going to be +4, because sometimes we overlook the number of them, right? So there's 4 of them. They're each -1, just like if they had ion charges. And so then the carbon has to be +4. But no, you would just need to say the chlorines are -1 oxidation state, the carbon is +4. And same here, we don't need to write both of them out. Whenever we have multiples of the same element, their oxidation states are going to be the same. You can imagine them fighting about who got to be different, right? It's not going to happen. Okay, SO3. This should not be confused with the sulfite ion, right? This is sulfur trioxide. It has no charge, it's a molecule. So we have 2 nonmetals. We're going to go Fe765. So there's no fluorine, there's no hydrogen, there's oxygen. So what is the oxidation state for oxygen going to be? -2. The same as the charge on an oxide ion. And so each of the oxygens is a -2 oxidation state. So what's the oxidation state of the sulfur? +6. Because there are 3 of those. 3 times -2 is -6, just like ion charges. And so the sulfur must be +6. Any questions about that one? So here's nitrate ion. So this is a polyatomic ion. It's got nitrogen and 3 oxygens. They're covalently bonded together, but overall it has an extra electron. So Fe765 again, no fluorine, no hydrogen, oxygen. So what does oxygen choose? -2. It always chooses that. And so then we have to figure out what the nitrogen is. So this is one where you might need to be a little bit careful. So I have 3 of these oxygens, right? I have 3 -2s. And then I have my nitrogen. I'm going to call that X because I don't know what it is. That's what I'm trying to find out. And those need to add up to the overall charge, which is -1. So then what is X? 5, +5. Any questions? So we can also identify oxidation as an increase in the oxidation state. The oxidation state went from a lower number to a higher number. It was oxidized. A reduction is a decrease or a reduction in the oxidation state. The oxidation state went down from more positive to less positive. So here, these are both free elements. Their oxidation states are 0. Here, CS2, 2 nonmetals, Fe765, we get down to the group 6 before we get anything. Group 6 is the sulfur. Sulfur's going to choose -2, like the charge on a sulfide ion. 2 of those, so the carbon must be +4. So now we can look at what happens to the oxidation state of carbon. It goes from 0 to +4. It's going up. That's oxidation. Sulfur goes from 0 to -2. It's going down. It's a reduction. This does not contradict oil rig. An increase in the oxidation state is a loss of electrons. Oxidation is loss of electrons. Reduction is gain of electrons. That's why it went from 0 to -2. But just a different way of looking at it. Any questions? Use oxidation states to identify the element that's oxidized and the element that is reduced in the following redox reaction. So we need to identify the oxidation states of all the elements here, which may sound a little daunting, but once you get the hang of it, it's not that bad. So here I have tin all by itself. What's its oxidation state? 0. Do I have any other elements by themselves? No, but here I have an ionic compound, right? Ionic compound, so this has tin ions and oxide ions. What's the charge on the oxide ion? -2. 2 minus. So the oxidation state is the same as the ion charge here. What's the charge on the tin ion? +4. So its oxidation state is +4. Same as the charges. The rest of these are non-metals. They don't have actual charges, and so we do Fe765. So fluorine in here, nope. Hydrogen's the next one, there's a hydrogen. So what does hydrogen choose? Hydrogen chooses +1. That's the charge it would have if it was an ion. So fluorine, hydrogen, the next one who gets to choose is oxygen. Just write it out like this. So here I've got a +1, and that's a total of -6, right? So that means that I have x minus 5 is equal to 0, or x is 5. So for the nitrogen, it's +5. Any questions? Oops. And then you can always, check it. So I've got +1 and +5, that's a total of +6. And here I've got 3, -2, so that's -6, it adds up to 0. So let's go over to the other side here. NO2, using Fe765, fluorine, nope, hydrogen, nope, oxygen. Oxygen's going to be -2. It always chooses that. So what does the nitrogen have to be? There's 2 oxygens, +4. This 4 coefficient in the front has nothing to do with it. That just tells us how many of those we have. We're just looking at this chemical formula, not looking at the coefficient. But 2 oxygens, each -2 would be a total of -4, so nitrogen's +4. And then over here, we have H2O, Fe765. There's no fluorine, but there's hydrogen. What does hydrogen choose? +1. And what does the oxygen end up having to be? -2. Does oxygen like that? Yeah, oxygen likes that. Okay, so we identified all the oxidation states. Now we want to see if any of the elements are oxidized or reduced. So we're going to look and see how things might be changing. We'll start with the beginning. So here, tin is 0, and over here, tin is +4. Is that an increase or a decrease in oxidation state? That's an increase in oxidation state. Bigger oxidation state means it's being oxidized. We could also think about this as losing electrons. That's why it's got a positive charge. So the tin is being oxidized. Let's look at hydrogen. Here hydrogen's +1, and here it's still +1, nothing happened. Here's nitrogen. Here it's +5, over here it's +4. So that's a change. Is that oxidation or reduction? It's reduction because it went down, it reduced. The oxidation state was reduced. So the nitrogen was reduced. Here, oxygen's -2. Oxygen is all over the place over here, but it's still -2. So nothing happened to the oxygen either. So we would say that tin is oxidized and nitrogen is reduced. The nitrogen inside that molecule was reduced. Any questions? Like I mentioned before, oxidation and reduction must occur simultaneously. If an atom loses electrons, there has to be another atom to take them. There's no homeless shelter for electrons. Okay, so all that is fine, and then we throw this wrench into the works. Agents. So there's things being oxidized and reduced, and then there's things doing the oxidizing and doing the reducing, and those are called oxidizing agents and reducing agents. And this is confusing, I'm sorry. The reducing agent has the element in it that's being oxidized. The oxidizing agent has the element that's being reduced. Not confusing at all, right? Okay, so let's think about movie stars. Movie stars have agents, right? What does an agent do for a movie star? Helps them find work, right? So the movie star stars in the movie. That's why they're called movie stars. And the agent does not star in the movie. The agent causes the movie star to get into the movie, right? So here, the reducing agent is not reducing. It's causing something else to be reduced. The oxidizing agent is getting the job for the oxidation. It's not being oxidized itself. It's causing something else to be oxidized. This is another one of those little tiny parts of Chem 1A. You could definitely do very well in Chem 1A, get a high A, and just completely ignore oxidizing and reducing agents. But I'm supposed to teach you about them, so there. So here, determine whether or not each reaction is a redox reaction. That is definitely something that will show up on an exam. And then for the redox reactions, identify the agents. Let's do the first thing first. We do not necessarily have to go and assign oxidation states to everything to figure out if this is oxidation or reduction. Let's first see if there are any atoms that are becoming ions or any ions that are changing their charges. So here I have lithium and chlorine, and they are forming lithium chloride. So over here, lithium did not have a charge. And here, lithium has a charge, right? Lithium in this compound is +1, and chloride in the compound is -1. Did electron transfer happen? Yeah, it did. Because how did lithium lose an electron to have a positive charge? It did so by giving that electron to chlorine, and that's how chlorine ended up with a negative charge. So this is oxidation reduction, a redox reaction. Let's look at this one. So here I have aluminum, and here I have aluminum 3+ ion. I have tin 2+ ion, and just plain old tin. Is there electron transfer happening? How can aluminum become an ion? By losing electrons. How can tin go from being an ion to being an atom? It had a +2 charge. How does it get rid of the +2 charge? By gaining back 2 electrons. So there's transfer of electrons, that's a redox reaction. This one looks like a mess. Well, let's see what's going on here. So you have an ionic compound and an ionic compound, and I'm getting 2 more ionic compounds. That one's a solid. This is one of those precipitation reactions. When we swap the partners here and put lead and chloride together, do they change their charges? They don't, because here was lead 2+, and we had nitrate ions. And in lithium chloride, we had lithium ions and chloride ions. This is what we did before we talked about all of this mess. And over here, we've got lead ions and chloride ions and lithium ions and nitrate. Some redox reactions are spontaneous, meaning they will happen, and others are not. So here we have a picture of a strip of magnesium in a solution containing copper 2 ions. That looks a lot like some of the solutions we saw in experiment 2A, right? So if we put the magnesium into the copper 2, what's going to happen is that the copper ions are going to form copper atoms, and the magnesium atoms are going to form magnesium ions. So we have this happening. The magnesium is getting oxidized. The copper is being reduced. If we do the reverse, and we put a strip of copper in a solution of magnesium atoms, nothing happens. Copper does not lose electrons to magnesium. So the activity series of metals is looking at metals in the order of decreasing tendency to lose electrons. So magnesium has a higher tendency to lose electrons than copper does. So copper's not giving its electrons up to magnesium. In the activity series, each of those reactions is written as a half reaction. And in the reverse, they would be a reduction. So here, if we could look at what if this would happen. So magnesium plus 2 electrons would give magnesium, and copper will give us copper 2+ plus 2 electrons. Here, the magnesium is gaining electrons. That's the reduction. Here, the copper is losing electrons. This is the oxidation. This is half of a reaction because those electrons have to go somewhere. If somebody's losing electrons, somebody has to gain electrons. If we combine these two equations together, we get a complete chemical equation. So 2 half reactions added together make a whole reaction. So this is the activity series. This is not all of the half reactions, but it's a bunch of them. You do not memorize this. Don't memorize that. And don't ask me either. On an exam, you'll be given enough information to answer the question. They might give you like 3 or 4 of these because you don't need all of them. They might not give you the whole chart, but they'll give you what you need. So the order here is that the one on top, lithium, is the most likely to lose electrons. So it's the most easily oxidized. And at the bottom, we have the one that's most difficult to oxidize. So we could say that this one has the strongest tendency to lose electrons. That also means it's more reactive than the guys at the bottom. Gold is good for jewelry because it doesn't react with a bunch of stuff, right? It's very stable. Lithium would be terrible for a ring because it would react with the sweat on your hand and just dissolve. Not good. Super reactive. Okay, so which metal is most easily oxidized? Sodium, chromium, or gold? Well, here we have this nice stuff over here, right? So that makes it easier. Yes?
Is there a reason for it to be in that order, or is it just is?
That's a good question. Is there a reason for it to be in that order? Yes, there are underlying reasons. They're not real simple to explain, though. Yeah. So we don't try to rationalize why. This was observed, and we're just going to use it. Yeah. But, we did learn that the alkali metals are highly reactive, right? And so here we see lithium and potassium and sodium up at the top. And the alkaline earth metals, calcium and magnesium, those are quite reactive, and so they're also near the top. So there's some correlation to things we've learned. Before we answer that question, well, let's see. Let's look at sodium and chromium. Okay. So sodium, these are tendency to lose electrons. So sodium is going to go to Na+, plus an electron. Chromium will go to Cr3+, plus 3 electrons. So let's say that we had solid sodium and chromium chloride. And those could become chromium plus 3 sodium chloride. I'm doing this because I want to show you how this relates to ions going to a party. Okay. So we talked earlier about, we looked at 2 ionic compounds, and we said, well, this is a guy and a girl, this is a guy and a girl. They're going to a party, they're going to mix and mingle, and if there's chemistry, we'll end up with a solid, right? So this is a little different. This is a guy and a girl going to the party. This is just a guy going by himself. They still call that going stag? No? What do they call that? Is there a name for that? You go to a party by yourself? On a date? Loser, maybe? Okay. Going stag sounds better. Anyway, sodium went by himself. Okay?
Oh, wait, no, solo.
Solo? Okay. Sodium's going solo, right? And chromium is taking a date. Now, these guys aren't necessarily like married or in a committed relationship even. They're just going together, right? So they go to the party and there's mixing and mingling that happens. And if a chemical reaction happens, chromium will go home solo and sodium will leave with the girl. Right? So if we look at oxidation reduction and see what would happen there, we've got the sodium, who came solo, is going to become a charged ion. You can also think of this, well, he was like neutral when he came solo by himself, and now he's got a charge. He's excited because he went home with a girl, right? And here we have chromium. Chromium's all jazzed and charged up because he's got a date for this party. And what would happen here is that he would go home by himself. So we have to figure out who's going to get the girl in the end. And this is very sexist. Sorry, it works. Well, this is a list of the guys in the high school in order of desirability. Okay? Lithium is the coolest. Lithium goes to a party solo, always leaves with somebody. Okay? Gold, almost never. You would think, right? But no. So, who's cooler? Who's more reactive, sodium or chromium? We're going to look on the list. Here's sodium, and chromium is down here. So chloride is looking at these guys, and she's going to pick the one that's more attractive, right? The more reactive one. And so she's going to pick sodium. So sodium leaving with the girl, this is going to happen. That's a spontaneous reaction, because sodium is more reactive than chromium. What if we switch this around? What if chromium's going solo, and sodium has a date, and then we're going to see sodium, sodium going home solo, and chromium leaving with the date. Is that going to happen? Well, if the first one happens, the second one's not going to happen because it's the opposite. But looking at this, here I've got chromium solo, chromium with a date. So this is saying that in this situation, chlorine chose chromium. Is chromium higher on the list? No, it isn't. This is not going to happen.
Breaks the law of oxidized dating.
Yeah. Chloride's like, I'm not going home with him. I came with sodium. He's a much better catch. I'm going home with him, right? We came together. I'm going home. I'm not leaving him, right? Does it make sense? Kind of? These things are hard to keep track of, and so this is actually how I think about it. Okay. So then, here, sodium, chromium, sodium, chromium, and gold, which is more easily oxidized. So we think of sodium. So we think about the oxidation that's going from the neutral to the charge, right? And so that's getting the girl. He's charged up because he's got the girl. And so we look at the list. Here's sodium, here's chromium, and gold is way down here. So sodium is the most reactive, the most easily oxidized.
Gold never gets it because they're a jerk.
Yeah, gold is kind of stuck on himself. Okay, determine whether each redox reaction is spontaneous. This is kind of what we just looked at. So here, the anion, the girl, is not shown in the reaction. But we can tell from the charges who's excited because they have a date, right? So here's zinc coming solo, and nickel has a charge. Nickel's got the dates, right? So is this going to work out that zinc goes home with the girl and nickel goes home solo? Well, it depends. Who's more desirable? The one higher on the list is going to get the girl and go home with the charge. So we're looking for zinc and nickel. So blah blah blah. There's zinc, and here's nickel. Zinc's cooler. Zinc's cooler. So here we have. Whoops. Don't know what happened there. My family is texting me is what happened, actually. It it's the texture family hour. Here, let's turn on Do Not Disturb. I should have done that.
Just do what I do and turn notifications off.
So here's zinc, and zinc's leaving with the girl. We looked at the list. Zinc is cooler than nickel. Is that going to happen? Yeah. Well, how about this one? Here, zinc getting the girl. I don't know what's going on. Zinc getting the girl in favor of calcium. Well, who's cooler?
Calcium.
Got to look at the list, right? So you guys were paying attention. Here's calcium. Calcium is cooler, right? So is this going to happen where calcium comes with the girl and loses her to zinc?
No.
Not going to happen. So this is not spontaneous. Does that make sense? Cool.
Not spontaneous is when they don't switch.
Doesn't happen.
Spontaneous is when
Mhm.
they switch.
Spontaneous is something that will happen all by itself, and non-spontaneous doesn't happen by itself.
So for the list, are we going to be given a list if we
Yes.
on that? Okay, cool.
You would be given either the full list or a partial list or some information. Yeah, you don't memorize that. I don't have it memorized. So
So is it not possible to happen, or just like
that's a
something else
good
has
question.
to happen?
So
for
is
it
it
to
not
happen?
possible to happen? It is possible to
It's
happen.
just unlikely.
But it doesn't happen on its own. It has to be forced. So the way you can force this to happen is using electricity. You can pump electrons into the calcium and pull them out of the zinc, and you can force this reaction to happen. But you can kind of think of that, well, we have to do some serious bribing of people, right? We got to put some money into this to make this happen. It's not just going to happen on its own.
Electrolysis, that's what that is.
Yeah, electrolysis. Yep, good question. Any other questions?